Now let's understand dehydration of alcohol. Now dehydration of alcohol is the reaction which includes the intermediate of carbocation. Let's say we have a molecule CH3. It reacts with concentrated H2SO4 and temperature which is greater than 100 degrees centigrade. It forms CH3, CH3, and forms double bond. It dehydrates the alcohol and water molecule gets out. So what is the mechanism behind it? What is the mechanism we follow in this reaction? So the mechanism that is being followed first is the fastest reaction in the world. One of the fastest reaction is acid-base reaction. So here we have H plus, and we have CH3C, CH3OH, CH2 and CH3. So first H plus will attack on OH minus. Acid-base reaction will happen. CH3C, CH3OH2 plus will form, and CH2 CH3. This particular compound is known as oxonium ion. So first of all, acid-base reaction which is reversible, this forms. Now second, we have CH3, this oxonium ion, CH2 and CH3, which is a rate determining step because this step involves the breaking of sigma bond. The sigma bond breaks, so that's why it is known as rate determining step, which is the slow step. It forms H2O plus CH3 C positive, CH3 CH2 and CH3. Third, we have this compound CH3, CH3 plus CH2 and CH3. Now this carbon has 3 hydrogen near to it. 1, 2, 3. 3 hydrogen it has, 3 type of hydrogen. Although we can say it is 2 type of hydrogen because these two are same. These two are same, but this hydrogen is different. So next, what happen? Elimination will happen. We are keeping on providing the energy to the reaction, then elimination will happen. Then CH3, CH3. What does it forms? CH3, CH3, double bond CH and CH3 plus H plus will remove. So it is more stable. How it is more stable? Because we have a second compound CH2 double bond CH3, CH2 and CH3. So when this hydrogen gets removed, we get this compound. When this hydrogen is removed, when we get this compound, this is less stable, and this more stable is known as Senzef product. Senzef alkene, and this is known as Hoffman alkene. Senzef alkene and Hoffman alkene. Now what is the characteristic of this reaction? Senzef alkene means a more substituted alkene, and Hoffman alkene is less substituted. Substituted we means by number of alpha H, alpha hydrogen. In the more stable alpha hydrogen we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and in less stable we have 5 alpha hydrogen. So what are the characteristics of the reaction? What are the characteristics? First, it is an elimination reaction. Second, RDS is a generation of carbocation. Third, we have rate determining step is directly proportional to the stability of carbocation. Fourth, we have it is an endothermic reaction. Endothermic means delta H greater than 0 and delta S is also greater than 0. Entropy increases. How entropy increases? From one molecule it is forming two molecules. So delta G equals to delta H minus T delta H. Delta H is positive, delta S positive. So entropy, it is entropy driven process. Means as we increase the temperature, as temperature increases, the reaction becomes spontaneous. Spontaneous at high temperature. Fifth, dH plus by dt equals to 0. Initially, how much H is now finally same as H plus is acting as a catalyst over here. Sixth, major product of reaction is most stable alkene. Major product of the reaction is most stable alkene, which is also known as Setsef alkene. Seventh, rate equals to K times concentration of oxonium ion. It is even. Now let's solve the problem. Compare a rate of dehydration of alcohol. Rate of dehydration of alcohol we have to compare. First it is, this is OH and this is OH. So which carbocation is stable? Our first carbocation is stable, then second is less stable because it is 3 degree carbocation and it is 2 degree carbocation. So first is having a higher rate. Then let's solve the second question. In second question we have 1 degree, 2 degree and 3 degree. So 3 degree has more rate than 2 degree and 1 degree. Let's solve the third problem. I am writing the problem. Just try to solve by your own. Take a pause and try to solve by own. So actually what we are doing, we are comparing the rate of the reaction, and when we compare the rate of the reaction, we check the stability of first carbocation, not the second and third. What do we mean by second and third carbocation? We mean by second and third carbocation by generating a carbocation and it gets rearranged. So I am just writing the question PHCH3 CH2OH. The first carbocation we have to check, not after rearrangement. Fifth, we have this carbocation and we have OH. Now let's check the answer. First of all, in first case, this is answer is 1, 2, 3 and 4. Because after generating this carbocation, it is going in resonance, which is a very extended resonance. It is less extended resonance. It is 3 degree. It is going in resonance, stabilized by resonance. It is not. It is 1 stabilized by resonance, 1 extended only, and it has 4 alpha H. And it is not going into the resonance because it is not going to break easily because that OH is involving in the resonance, and this bond is having partial double bond character. So it is tedious to break. It is difficult to break. Now in second case, the stability of carbocation. Third, the bridge-hand carbocation is very hard to generate. It is impossible to generate the bridge-hand carbocation. So that's why the answer is this. Now let's check the sixth question. We have that OH and we have this OH. So which gonna stable? The first is more stable. Then we check the second, seventh. In seventh we have this compound and this compound. So first is more stable because it has more alpha H greater than its alpha H. Now write the energy profile diagram. Now write the energy profile diagram of the reaction. Energy profile diagram. How does the energy profile diagrams look like? Let's say first of all we are converting this into alkene by reaction H2SO4 concentrated and delta. So first of all H plus will go. First of all acid base reaction will take place. OH, this will react with H plus and it will form OH2 plus. Second we have this OH2 plus oxonium ion reacts with forms water. And third, now this when this form water, now what happen, the carbocation rearrange, then it forms two product, one is major and one is minor. Major is A, minor is B. Now let's draw the energy profile diagram. We have energy profile diagram. We have E energy. So first of all, what happens? Carbocation attacks. Carbocation attacks. Now in second case, the carbocation first of all H plus attacks, so it forms oxonium ion. Now it require a very high energy. Now it require very high energy. Now E is very high. It will form a positive charge. Then the cation will rearrange. The cation will rearrange. Now H plus. Now it form two product B and A. So A is more stable and B is less stable. So that's how we check the energy diagram. It is time versus E. That's why we draw the energy diagram. Let's draw energy diagram for one more compound. First we have PHCH, CH3, CH2 and CH2, then OH with concentrated H2SO4 at 170 degrees Celsius. It will form PHCH, CH3, CH and 2 CH2 plus. The carbocation will rearrange CH plus and CH3. Now carbocation again will rearrange CH two and CH3. Now this will form two products. One is major and one is minor. Major one is this is major, which is also known as HF, more substituted, and PH, C double bond CH2. This is minor. So first we have a major product, then we have a minor product. Let's draw the energy diagram. How many carbocation are rearranging? First, second. Two rearrangements are there. So two rearrangements are there. Let's draw its energy profile diagram. Its energy profile diagram. First it will form oxonium ion, then it will form first transition, first carbocation, then it will form second, then it will this is first carbocation, then second. Here first carbocation it rearrange. Now again it's rearrange and it forms two different products, B and A. Minor is B, major is A. Now number of transition state 5. Number of intermediates 4. We have 4 intermediates. 1, 2, 3, 4 intermediates we have. Now this is the reaction. 1, 2, 3, 4 intermediates we have. 1, 2, 3, 4 for B, 4 for A. Now we have to check, do both types of questions. Now let's say we have to check compare rate of dehydration. We have to compare the rate of dehydration. How does we compare the rate of dehydration? Let's say we have CH3, CHOH, CH3. Now we are comparing it with CD3, CHOH and CD3. Now here what happens, the carbocation will be same. Carbocation is after generating the oxonium ion. This oxonium ion will generate the carbocation. So the carbocation will be same, and hence kinetic isotopic effect is not applicable. So kinetic isotopic effect will not be applicable over here. Kinetic isotopic effect is what, when we interchange it with another isotope and then we check the rate of the reaction. And so in this case the rate of the reaction will be remain same. So let's solve some problem of this reaction. First of all, we have OH. All the reactants are concentrated H2SO4 and temperature 170 degrees centigrade. So what will happen? The generation of carbocation will be there. Now it will rearrange. Now it will form alkene. That's how we have to solve the question. So I am writing the question. Just take a pause and try to answer by your own. Now it will be generation of carbocation. Carbocation will be here. It will be having two products. This is major and this is minor. Third, again same reactant we have. So the carbocation will form. It will rearrange. Now it will give the two product. This is major, Sedzef, and this is minor, Hoffman. So actually sulfate ion SO4 minus 2. It is a stable ion. So does not react with. So it doesn't react with carbocation. So it is a very stable ion which doesn't react with carbocation. Let's say we have first this compound OH. So this will form positive charge and it will give this compound, and another compound it will give this, and one more it can give compound. This is trans and this will give the cis one. So how many different products are there? It has 3 different products. It has 3 different products. Second we have OH, concentrated H2SO4 and this. So it will form, I am writing the direct product, Sedzef and Hoffman. So I am writing question and answer. You have to try by your own and check the answer. Sixth, it has 5 transition state in this compound. Carbocation will generate here, will come here, will come here. Hoffman this is, and this is Sedzef. So if you draw, you will get 5 transition state. Seventh, this is Sedzef, this is Hoffman. You will get 4 transition state here. Here you will get 3 transition state. This is Sazab, this is Hoffman. 9th. You will get this product over here. 10th. Actually the carbocation will come here. It will expand. This will rearrange and this will form 2 products. This one. This is major and this is minor. Now we are not counting the transition state. It will be very lengthy for it. We have OH here. So first of all the carbocation will generate. There will be generation of carbocation. Now ring will expand. Now benzene will form. 12th. It will form this compound and this compound. This is major. This is minor. 13th. Just try by our own. The answer will be major, minor. 14th. We have all done this type of problem in rearrangement of carbocation. It will be having 2 products. Major, this is major and this one is minor. 15th. H plus will attack here. It will be having 2 products. Sedzef, Hoffman. 16th. Sedzef and this will having Hoffman. Now last we have 17th question. First H plus will the after 7 transition state. This all question are repeating after the rearrangement of carbocation. The phenyl we have final carbocation will come here. It will have 7 transition state. Now final product will be this one.